go.
Hello, my dear students, and today for me is a special day because it's my wife's birthday. It's also International Mole Day, October 23rd. I don't know what's going to happen to our class, and I don't know what's going to happen for our future, but today I want to cover this nomenclature worksheet from ChemLibre, or LibreText, but it's ChemLibre. It's the free chemistry textbook website. I will include that link for you. I've done it once before. In whatever career you go, engineering, chemistry, science, and you take chemistry in college, all the way through all graduate chemistry and biochemistry, there are free textbooks as part of a joint university from the joint program by the National Science Foundation and the University of California system. That's UC Berkeley, UC Riverside, UC San Francisco. All those great colleges have written chemistry textbooks from outstanding authors and chemists that are used everywhere. You'll see when you go to the website. Anyway, but it had some questions. We did the first page, questions 1, 2, and 3. Putting compounds together to form a neutral compound. Naming compounds given the formula, and given the name of the compound, providing the formula. Now I want to do the second page of this, which is taking those compounds, now that we name them, now that we have them, and doing some simple calculations. So I want to do question 4 today, and in the next video I'll do question 5, okay? Which is calculating empirical formulas. It's kind of like doing average molecular weight and isotopic composition. It's just something you should see how it's done. But this is important. This is using a mole map, calculating moles from formulas and molecular weights, and calculating quantities. It's what we do. So you got to master this. So I'm going to try and go through it as slowly as I can. The first one says, well, in general, it says calculate the following quantities. The mass in grams of 0.773 moles of calcium hydride. Calcium, it's group 2, it's always plus 2. Hydride. Hydrogen can be plus 1 or it can be minus 1. In this case, it's minus 1. This is plus 2, so I need 2 of these. If you look in a standard periodic table at those atomic, elemental weights, in this one they are called average atomic mass. It's the big red number in your Flynn periodic table and the one up on the board. It's also usually the biggest number in any periodic table, except for maybe the element number itself. So if I go there, I see that calcium right here is 40.078. Forget atomic mass units, AMU. And sadly, you can forget about Daltons because everybody else has, and they don't really use that terminology. But here's what that number really means. That's the number of grams in 1 mole of that pure element. So for calcium, it says 40.078. I added the units grams per mole. You notice here in the Flynn table, it's unitless. And I said later on, we'll see how useful that number is. Hydrogen is 1.00795, but there's 2 of them. So I multiply that times 2, that's about 2, add it to 40, and I get about 42. When you add it all up, if you want to use all these significant figures that they're given, it's 42.9039 grams per mole. So here's how you solve the problem. I needed my molar mass, my molecular weight, my atomic weight. Well, it wouldn't be atomic weight because these aren't atoms, but you need your molar mass of this compound, and that's what I did. It has 1 calcium and 2 hydrogens. So I took the weight of 1 calcium, 1 mole of calcium, and the weight of 2 moles of hydrogen, and I just added it up. That's all I did was sum that. So now I take my information. I have 0.773. It wants to know the mass. Use your mole map. I have a kind of a funky mole map here. It's got a little mole in it here on International Mole Day, but I need to convert from mass to moles. So I'm given a mass. No, they want me to calculate the grams. So I have moles, and I need to convert to grams. So what do? If I'm going with the arrows, I multiply. So I multiply by the formula weight. That's what we just calculated. The formula weight's 42. So if I have 42.093 grams per mole, and I only have 0.773, it's going to be some fraction of that. I multiply them, use my mole map, and do it. And when I do that, let me use a different color for my answers. I get, it's going to be less than 42, right? Because it's less than a mole. It's less than 1. And the answer is 32.5 grams. Because they want the mass, and they gave me 3 significant figures here. Yes, I know these atomic masses out very far, but this was my answer. So now for the next one, they ask a little different question. This time they're going to give you the mass in grams, and they're going to ask you for the number of moles. So in our mole map, they're giving us the mass in grams, and we want to convert to moles. So this says divide when you're going against the arrow. So this time I'm going to divide by my formula weight. But I'll show you how that works out when I get to the end. So this is magnesium nitrate. Nitrate is a polyatomic ion. It has a -1 charge. Magnesium, like calcium, is a group 2 metal. It's always +2. If you can't remember, look at the periodic table in the classroom. You'll see I've written a +2 above the group 2 alkali earth metal elements. So magnesium has a molar mass of 24.3051 grams. 24.3051 grams per mole. Now, in this nitrates, I've got 2 of these nitrates. So I've got 2 nitrogens, because each one has 1. So it would be 2 times 14.0067, or about 28. So 24 plus 28. And I'm going to have 6 oxygens, because each nitrate has 3, and I've got 2 of these nitrates. So I take my molar mass for oxygen, which is about 16, 15.9994 grams per mole. Multiply that by 6, and if you add all this up, you get a molar mass of 148.3149 grams per mole. Much greater precision than we need for this, because they said you have 5.35 grams. So when you solve these, you write down what they gave you. They gave me 0.773 moles. And I wanted grams. They asked me for the mass. So I needed to do 42.939 grams for 1 mole. In this example, my moles cancel. I ended up with grams. In this example, I flip my equality. Remember, this equals 1. These are the same things divided by each other. So it's 1 over 1. 1 mole corresponds or is equal to 148.3149 grams. So now I have, oops, I didn't need that part of this. 1 mole is equal to that many grams. So now my grams cancel, okay? And I have moles, 1 mole here. So my moles, my units are going to be in moles. And if you do the math, 5 divided by, what, 148.3149, you get 0.0361. 3 significant figures. I can't use all this stuff, the calculator vomit that you're calculator is going to throw out, because I can only really have 3 sig figs moles. If you want to be precise, or if you've forced your calculator into scientific notation, 1, 2, this is 3.61 times 10 to the minus 2 moles. And there's your answer. Okay? We're going to go a little more slowly because I don't have the next few problems done out. So I'm going to write as I go. But I want to get through these as quickly as I can. Already done my calculations and everything. So for 4C, it asks for the number of molecules in 0.0305 mole of this compound CH3OH, which I believe is methanol. Okay? I don't believe, I know. Or methyl alcohol. Here's its structure. When you have an OH, that makes it an alcohol, an alcoholic OH. It's also called a hydroxyl group. So, this is methanol. I don't need my formula mass. It wants the number of molecules in that amount. So I know that 1 mole, well, write down what you know. I have 0.0305 mole of methanol. CH3OH is really the way I was taught to write it. You can write it CH4O. But this gives you some structural information about it. And then I use my mole math. They want number of molecules. I know that there's 6.0224, if you, however many places you want to take it out, times 10 to the 23rd molecules per mole. Molecules of methanol, if you want to carry this out to extremes, per mole, per 1 mole of CH3OH methanol. So my moles of methanol cancel, and I end up with molecules. And if you do 0.0305 times Avogadro's number, 6.02 times 10 to the 23rd, what I got was 0.18 times 10 to the 23rd molecules, which is also corresponds to, put it in more accurate, this is not a legitimate whatever scientific notation, so 1.8 times 10 to the 22nd molecules. Molecules, not moles, molecules now. A lot of molecules in that 0.03 of a mole. Okay? So, what else can I do here? That does it. So, the next one is for D. It says something crazy. Number of carbon atoms in 0.585 mole of C4G10. Oops, G10. And there is no such element as G. There's germanium, there's gallium, I can't think of any other G ones, but I'm sure there's some other ones. There's no such element as G10. I think they meant H10, which would make it one of the butane molecules or something. But G is close to H, I don't know. But the point is here, we don't need that information because I want the number of carbon atoms. So, you know, my point is that for this, for there's 0.585 times 4 moles of carbon atoms, okay, per 0.585 moles of this weird compound, C4G10. I don't know what the typo there is. They should have hired me to prove this. But if you do 4 times if you have 0.585 moles of this compound, and there's 4 moles of carbon atoms, for every mole of that, there's 4 carbon atoms in every molecule, and therefore 4 moles of carbon atoms in every mole, it would just be, 0.585 times 4, which would be, what? I wrote it down here. This is 4D. It says number of carbon atoms. Okay, so there would be 2.34 mole of carbon and 0.585 moles of this compound. But they asked for the number of atoms. So I have 2.34 mole of carbon and 0.585 moles of C4G10. And I know that there's 6.02 times 10 to the 23rd atoms of carbon per mole of carbon. And if you do the math, 2 times 6 is about 12, but it's 2.3. And when you do the math, you actually end up with 14.09 times 10 to the 23rd carbon atoms. And that is not a legitimate scientific notation for that value. So, we're just going to change it to 1.4. I'm only allowed 3 significant digits, and this has 4. So 1.41 times 10 to the 24th carbon atoms. That's your answer, okay? That's 2 more. I didn't have to calculate my molar mass. I could work the problem even with an imaginary element, G, and it still worked. So let me go back to my black pen. 4D, 4E, we have EFG, 3 left. It says the mass in grams. So in 4E, the mass in grams of 1.906 times 10 to the minus 2. So that would be like 0.019 moles of barium iodide, I2, BaI2. Okay? So they want mass, so I'm going to need my molar mass. So barium, if you look on the periodic table, it's a very heavy one. It's used a lot in medical imaging because it is so electron dense. It's so, it shows up as opaque on X-rays. So it's used in X-ray a lot. It's 137.327 grams per mole. And I'm going to make another comment about these formulates. And the iodine is group 7. It's a pretty heavy element too, 126.904 grams per mole. But there's 2 of them because this is always -1 and barium is always 2+ because it's group 2. If you see barium, it's down here, and if you see under the valence, it's always a 2. Iodine can have various ones, but the -1 is in bold, so it's the most common. And really, the group 7s are really just all -1, except later in the course when we might use some different charges to talk about some bonding. Now, so I need this times 2. And I went ahead and did the math. And if I look up this, well, not look up, but if I do the math, my barium iodide BAI2 is equal to 391.135 grams per mole. Now let me tell you, this wasn't too bad because I can get on my calculator, punch these numbers in, multiply this times 2, add it to that, add up all the atoms, the masses of all the atoms in this compound, and get my compound. But if you have a more complex compound, as we might work with in the next couple problems, it takes a while to do that. And if you're using your phone for a calculator or you have a laptop open, you can just Google barium iodide. You can Google BAI2. And it will come up with some information on that compound, its safety, its uses, its history, but it'll always give you the molecular molar mass. And it's almost quicker than doing it. Plus, I'm going out to all the digits that are available to me in my periodic table with that red number. You know, they have 4 digits here, so why am I doing 6 here and 6 here when I really only need to do 4 to, you know, because my sig figs can't go beyond that anyway. Okay, so I have this molar mass and I have this many moles. So again, I write down what I know, 1.906 times 10 to the minus 2 mole times, I want to get rid of my moles, so times 1 mole per 391.135 grams. Oops, I did that wrong. Times, I want to get rid of my moles, so I want moles in the denominator here. So I'm going to write this over. 906 times 10 to the minus 2 mole times 391.135 grams, because it wants the mass in grams, per 1 mole. And now my moles cancel, and I multiply. The other thing is, I was given number of moles and it mass for grams, so if I go with the arrow, I multiply by my formula weight. That's my formula weight. So use your mole map or set it up so that you end up with the units you want in the numerator. And our units here, if you do the math, 0.01906 or 1.906 times 10 to the minus 2 times 391, you will end up with 7.46 grams of barium iodide. And that's my answer, and I'm sticking to it. Okay? Now, for 4F, 2 more. For 4F, I'm going to have to calculate the molar mass, so I can do the next 2 very quickly on one sheet, because the last one's a shorty too. 4F involves this compound, ammonium chloride. Ammonium is NH4+, it's a polyatomic ion, and chloride ions, of course, are group 7 chlorine with a -1 charge, has 7 electrons in its outer shell. Wants to have 8. It picks up 1 extra electron with a negative charge, so it has a 1- charge. Ammonium ions are here. So this is this compound, ammonium chloride. And the question asks, number of moles in 48.3 grams. So if you look at your mole map, it's going to ask you to divide this by the molar mass. So I need my molar mass. So if I do this, Nitrogen is equal to 14.0667 grams per mole. Hydrogen is equal to 1.00795 grams per mole. But I have 4 of them, so I need to multiply that by 4. And chlorine is equal to 35.453 grams per mole. These are the big red atomic masses, average atomic masses, in your periodic table for my formula. So if I add all this up, 14 plus 35 is what? 49 plus 4 of these is 53 and a half, because this is actually 35 and a half, not 35. But if you do the math and add it all up, you get that ammonium chloride has a molar mass of 5515 grams per mole. Now, when you go to the internet and you look up this molar mass, it might be 0.56. You might say, well, that should round to 0.55. They might have used a different or an older periodic table. They might have used a newer periodic table with better molar masses out to more digits. You might find some variation when you get out, past 4 or 5 significant figures, but I promise you it won't make a difference in your final answer. Anyway, using your mole map, I have 48.3 grams of ammonium chloride, and I want to get rid of grams and have number of moles times 1 mole of ammonium chloride per 53.5515 grams of ammonium chloride. So my grams of ammonium chloride cancel, and I'm left with moles. And my answer here will be, if I can get a different color. I set it over here. We go. You can see, it's going to be less than a mole, because a mole weighs 53 grams and you only have 48. And that's exactly what my answer says. 0.902 moles of ammonium chloride. 9/10 of a mole. With 3 significant figures, because even though I know these molar masses out this far, the mass that I measured is only that. The number of moles I should have written in 48. And finally, for G, they give this weird compound, HCHO2. Chemists crack me up. I'm a biochemist. I would write this as HCOOH, because this is formic acid. A very simple acid. It's actually the acid in the bite, the toxin in the bite of Solenopsis, which is the fire ant. So, Solenopsis invicticus, I believe, is its name, genus and species. But this has a structure, hydrogen, with a double bond O and a OH. And this H can pop off. That's what makes it an acid for the pH there. So this is formic acid. I've never seen it written this way, but chemists just put things down. And it doesn't matter. Hydrogen's 1, carbon's 12, oxygen's 16, but we don't need that, because it asks us in our question number of molecules in 0.05752, someone measured this very accurately, moles of formic acid. HCOOH. That gives me a better idea of its structure. So, and if you use your mole map, you know that to go from moles, they gave you the moles, to number of particles, atoms, molecules, or formula units, you multiply times 6.02 times 10 to the 23rd times 6.02 times 10 to the 23rd molecules per 1 mole of formic acid. So my moles cancel, and I'm left with molecules. I don't really have enough room to write my answer, but if you do that, you get, I got 0.346 when I multiplied 6.02 times 0.05752. And of course, my powers of 10 would still remain times 10 to the 23rd molecules. That is not a legitimate molecules. That is not a legitimate scientific number in scientific notation. I need to change that to 3.46 times 10. So I'm going to go there, right? Times 10 to the 22 molecules. That's your answer. We're going to work this question 5 on doing the empirical formula for those 3 compounds next time, in the next video. And then I want to go back and show you in another video that I've prepared how to work the problems from the old final exam, which are exactly like the ones you're going to get, except maybe a different reaction. So until then, finish this question 4 with those A through G. Write them neatly on a piece of paper. Show your work. Don't forget to include units, molecules, moles, grams, whatever it is. And I will see you in the next video. Goodbye now.